Welcome back to this lecture on morphological operators. Morphological operators are sets of kernels that can achieve a variety of effects, such as reducing noise. We've already seen kernels that can achieve effects such as blurring and smoothing. These morphological operators are going to expand on that. In fact, certain operators are very good at reducing black points on a white background and vice versa. Other types of operators can also achieve an erosion and a dilation effect that can add or erode from an existing image. This effect is actually most easily seen on text data. So what we will be doing is we're going to practice various morphological operators on some simple white text on a black background. Let's get started. Welcome back. I'm going to copy and paste a few functions from our morphological operators notebook. The first function is a function that loads the image. And before we actually load up these functions, what I'm going to do is also copy and paste all our imports that we usually do. So import cv2, numpy, and matplotlib. I've copied and pasted these imports from the morphological operators notebook. I'm also going to copy and paste this load image function. And what this does is it loads up 600 by 600 zeros, so that's just a black image, and then we write some white font on it that just says ABCDE. And then what I also want to do is display the image so that it's a little larger. I will copy and paste the display image function as well. We've already seen this function quite a few times. And then let's go ahead and load up the image and display it. So I will say image is equal to load image, and then we will display the image with display image. And when you run that, you should see the result of this, kind of these balloony-like letters of A, B, C, D, E. Okay, so we're going to learn about a couple of morphological operators. Essentially, they're just specialized kernels to achieve a specific effect. So the first one we're going to look at is erosion. And erosion, as a morphological operator, essentially erodes away boundaries of foreground objects. So here we can see that the letters look to be in the foreground, where the black is a general background. And what we're going to try to do is, with this kernel, detect these edges between our foreground text and the background in black, and we're going to begin to erode away that boundary. The kernel we're going to create is kernels equal to np ones, and we'll create a 5x5 kernel, and we'll also specify the data type to be integer, so np uint 8-bit integer. So if we take a look at that kernel, it's just a bunch of integer ones. Okay, then the next thing we're going to do is call cv2.erode, and then you pass in the image, and you pass in this kernel, and you can play around with the actual size of the kernel. And then the last parameter you can pass in is iterations, which essentially means how many passes you want to do. So we're going to say first iterations equals to 1. So iterations equal to 1, essentially doing one pass, and we'll call this result. We'll run that, and let's display that actual result. We'll say display image result, and here we can see the actual letters. Do we actually see any erosion here? Well, if we take a look at the original image, you'll notice that the connection between A and B is quite strong, and here it begins to weaken. Let's actually see an extreme version of this. We're going to load the image again. So let's reload this image here. So I ran that cell again so I can display the image. And same kernel, I'm going to be using this 5x5 of all integer ones, except now I'm going to do 5 iterations. So this should be a pretty extreme effect, and maybe I don't want it that extreme. Let's do 4 iterations, just in case we lose the letters off at our 5. But I'm going to display the image as a result, and you can see here that now we've definitely eroded away quite a bit from the foreground text. So that's how you can perform erosion, which is a morphological operator. Again, you just say cv2 erode, pass in the image, pass in a kernel of your choosing of ones here. You can play around with the different sizes, 7x7 or 9x9, but typically the thing you're really going to be editing is this iterations. If you want more erosion, you just do more iterations. Okay, then the next effect we're going to learn is opening. Opening is erosion followed by dilation. So dilation is essentially the opposite of erosion. You end up adding more to that foreground. But what's useful about opening is it can actually be helpful in removing background noise. So what I'm going to do is I'm going to create some white noise and put it onto our original image. So let's load up the image again, essentially that white on black text. And then I'm going to create some white noise using NumPy's random capabilities. We'll say np random rand int, and we'll say the low is 0 and just the high goes up to but not including 2. So this is essentially just going to give me ones and zeros. And I want the size to be equal to 600 by 600, the shape of our original image. Which means if I actually take a look at white noise, it's an array of 600 by 600 points of either zeros or ones. Which in our case, since we're dealing with just zeros and ones here, it's all binary, then this is essentially just a bunch of noise. So if I actually display this image, if I say display image white noise, it's just a bunch of noise. So random spots of black, random spots of white. What we're going to do now is actually end up putting in this white noise into our original text image. The way we're going to do that is if we actually take a look at our original image. So right now our image, if we check out the max value, it ends up being 255. So we need to convert this to be zeros and 255s. So what we will do now is say white noise is equal to white noise times 255. So now it's just going to be a bunch of zeros and 255 points. So zeros and 255s. That way it's going to be at the same scale of our original image. So we still have a bunch of black and white. We can still display this image. Display image of that white noise. And there you have it. It's still a bunch of noise there. Now what we're going to do is we're going to say noise image is equal to white noise plus our original image. And if we say display image and pass in the noise image, now you'll notice that it's become a lot noisier. So we just essentially added in all those values of 0 and 255. So some points got some noise, some points didn't, but here we can see that it's kind of a mess. So this is our noise image. We just ended up adding all this noise to the original text we had up here. Now we can use opening, which is a technique as a morphological operator, to actually get rid of this noise. So if you ever have a situation that looks something like this, where you have kind of a dark background and a light foreground, but it ends up being very noisy, specifically black and white noise in particular, so this works really well on grayscale images, then you can use this morphological operator. And this is called opening. We're going to say CV2, and we call morphology EX. You pass in the noise image, and you'll say CV2 morph underscore open, and then you'll pass in that same kernel we used earlier. Run that, and then display the image. And you'll notice right away that we were able to essentially clear out a lot of the noise without too much distortion of the original text. If we actually see the original image, if I say display image and show the original one, you will notice that it wasn't a perfect rendition. So here's the image that's the original one. Look at the B there. Look at these two kind of holes in the B. And if you look up here, you can see there's a little bit of noise, and that has to do with the way that the opening wasn't able to perfectly clean up these letters. You can see the E still has kind of extensions off its original boundary compared to the flat image here. But it was able to do a really good job considering just how much noise there was in this noise image. Okay, so that's known as opening. And again, all opening really is, it's just erosion followed by dilation. So we've already seen how erosion works, and dilation essentially just expands on the image. So we're going to come back down here. So that's known as opening. And again, opening is really useful for getting rid of noise in that fashion. So it's useful for removing background noise. Now, in some cases, you're actually going to have foreground noise. And we're going to now create an image that has foreground noise. I will reload the image again, just so we start fresh. And this time, instead of white noise, I'm going to create some black noise. And we'll say np.random.randint. The low is going to be equal to 0. The high is going to be equal to 2. Let's write that in. Whoops. High will be equal to 2. And then size is equal to 600 by 600. And the reason we say high is equal to 2 here, that's the upper limit. It doesn't actually include the upper limit. And you can check that by saying Shift-Tab. The upper limit high is exclusive. It's not inclusive like the low one. So this is going to end up being our black noise. And if we take a look at it right now, it essentially looks as the white noise, at least what we started with. But what we're going to do now is say black noise is equal to black noise times negative 255. And if I take a look at the results of that, notice now I have zeros and minus 255s. So that's not going to affect the black, but it will affect the foreground in white. It'll make some of this back down to black. So what we're going to do here is the following. We're going to say a black noise image is equal to image plus black noise. So then if we actually display this, and actually we're not quite done yet, if we show the image, black noise image, notice right now it's a bunch of zeros and then negative 255s. So what we're going to do is anywhere it equals negative 255, we're just going to bring that back up to 0 because that doesn't really make sense for a value. Everything should be either 0 or 255. So we can simply do this with some indexing. We'll say black noise image, where black noise image is equals negative 255, set that equal to 0. And now if I take a look at the black noise image, specifically the minimum value, it's now been turned to 0. So we took all these negative 255s and brought them back up to 0 because 0 should be the smallest value we have when displaying a black and white image. And essentially what this black noise did is it's going to randomly subtract 255 from every single pixel in this original image. Now for the black ones, which are 0, that means they go to negative 255. For the white ones, that means they go down to 0. So then we're just taking everything that went down to negative 255, the black foreground, and bringing it back up to 0, its original value. So let's actually display the results of that. Display image, we'll say black noise image. And notice now what we have is essentially just a bunch of black points in the foreground. And we can use closing to actually attempt to clean this up. So previously we had a bunch of noise in the background. Now we have a bunch of noise solely in the foreground. And closing is a good way of getting rid of this sort of noise. We'll say closing is equal to CV2, and it's essentially almost the same call, morphology EX. Just tab autocomplete that. You pass in your noisy image that has a bunch of noise in the foreground, and then we'll say CV2 morph underscore close. And then you can pass in the same kernel. And you can experiment with different kernel sizes. Some may be a little noisier than others. And let's display the results of that. We'll just say display image, show the results, and there it is. Notice again, it's definitely not perfect. Now you can see there's some lines that are much stronger. The connection between A and B is actually a lot thicker now, and now there's even kind of a thin white line between B and C. However, given how much there was to work with here and how much noise there was, it's actually doing a pretty darn good job. And you can experiment with the kernel size in case you want to try to see a kernel that's better. But in general, this is the way you can get rid of foreground noise, morph close. Essentially the opposite of morphological opening. Okay, now the last thing I want to discuss is the morphological gradient. And the morphological gradient just takes the difference between dilation and erosion of an image. Let's reset our image. We'll say load image. And all we're going to do here is display the original image so we can see what it looks like. So here is the original image. We know that if we were to perform erosion, it would begin to get rid between the background and the foreground edge. If we were to perform dilation, it would actually end up adding more, making these letters even more bubbly. The morphological gradient will take the difference between those two. And what happens is, especially with text, it becomes really clear. You essentially just grab the edge of the foreground next to the background. And this is kind of a method of edge detection. So we'll see more sophisticated methods of edge detection later on in a couple sections further down in the course, but this one's pretty simple. We just say gradient, and then say CV2, again, calling morphology EX, say image, CV2, and this time the morph call you're going to do is morph gradient, and pass in the same kernel. And this will be a pretty cool result. We'll say display image, gradient, run that, and there you have it. This is the difference between erosion and dilation, essentially just the edges of this text. So you can do this as kind of a crude form of edge detection. And that's it for all the morphological operators that we're going to cover in this lecture. We'll see them come time to time, especially when we need to get rid of noise, and then we can even add them in with things like median blur to also help get rid of noise in certain images, or maybe help with edge detection. But that's all you need to know. The fact that you can, don't worry too much about adding noise to images. We really won't be doing that. What you should understand though is that there's different calls you can make, And those calls are essentially in this format. If we come back down here, they're morphology EX, you pass in the image, and then you do a CV2 call with a morph underscore, and it's either going to be open, close, or gradient, depending on what you're actually trying to achieve, and then you pass in the kernel as well. And you can play around with that kernel size. Okay, so that's it for this lecture. We'll see you at the next one where we dive in deeper into gradients.